Hello everyone. In the previous lecture, we had derived the formula for finding uh, the deflection corresponding to a point force using the Castiglione's theorem, and the specific form that we had arrived at pertained to the case of beams. So let us look at an example in this lecture, a very simple example, something you are all very familiar with. So this is the case of a cantilever beam loaded by a point force at its tip. So the diagram is something like this. We have this beam here, and let's draw the tip load. Just like this, acting vertically downward at the right end, and of course the beam is attached to a wall, is clamped to a wall at the left end. Okay, so maybe something like this. All right, so that represents the wall. Now what we wish to find out here is the deflection at this tip, and please note that when I say deflection, I specifically mean the deflection along the direction that this force is pointed, that is in the vertically downward direction. Okay, so the formula that we had derived in the previous class after a lot of discussion, after a lot of build-up, was this: UF bar is equal to, so we can just take a quick look at what we had found last time. So all this discussion was regarding the regarding the material behavior. We don't need that, that was for our knowledge, but this is the formula that I'm referring to. Okay, so this is the formula for the U, the strain energy. So we are going to use this thing. Okay, and okay, so suppose this this force is represented by this P. So for all intents and purposes, this is P. So this is del P of U, and U, as we had found out, as I have just shown you from our previous lecture, that was m square by twice EI dx, 0 to L. Please note that this entire length here, this entire length, that is L. Okay, so now the first question, obviously, and the most important question in these problems is that what is M? So for that, what we are going to do is we are first going to fix up our the origin of our coordinate system. It is completely up to our choice. So for this kind of a cantilever problem, if you think about it a little bit, it becomes very easy if we just set up our coordinate axis at the right end and go leftward to account for the positive direction of x. So we say that it's something like this. So this is our x. Now what we are going to do is make a cut like this and consider that portion of the beam. Okay, consider that portion of the beam. Where of course this P is again acting downward. Maybe I need to clear up my overall picture here a little bit. Just for the sake of clarity, I'll just bring it down a little bit. Okay, so what we say is that, and again this is directly following from our undergraduate studies, that the shear force here will be directed upward, and the bending moment is like this. Now it is not completely arbitrarily that I am drawing these conventions. There is a certain reason and logic behind this. If you're paying attention to what was taught in your undergraduate days, you will immediately pick up on what I'm saying. But in case some of you are not very comfortable with this convention, and I think I may have discussed this in our previous course on applied elasticity also. Nevertheless, if you're still confused with it, please don't sweep it under the rug. I mean, we can discuss this in one of our live sessions. So there is a note for the students enrolled in this advanced mechanics of solids course. I won't invest time on this, but just for the record, we all know this from our undergraduate studies. So M, okay, so this M is equal to minus Px. Okay, so please note that what I'm actually writing here is that this M here, this M, so this is M in the clockwise sense, and the moment of this force P about an axis passing through this end, where this distance of course is x. So this distance here is x. Okay, because we are counting x from the right hand side. We are measuring x from the right hand side. So this is so the moment contributed by the force P about an axis which is passing through this end is Px, and it is in the same sense as this M. So it is actually M plus Px is equal to 0, and that gives us M is equal to minus Px. Okay, but that of course doesn't clarify why this should be in this sense. Okay, you can take this in the opposite sense. It won't make any difference to the answer, but this is the convention. Okay, and there's a reason behind it. Anyway, we don't have to worry about the shear force now. It is there for the force balance. Now we can substitute it back here to find out our UP bar. Okay, so our UP bar is equal to del P, and over here we can just substitute this thing. So it will be P square x square by twice EI dx, and this please note that of course I have to write the integration limits. So this del P can be taken within this integration, so that overall what we'll have is this integration 0 to L P x by EI dx, because this is a square. All right, and if we carry out the integration, what we'll obtain is Px cube by 3 EI with the proper integration limits. What we'll end up with is this very familiar answer, PL cube by 3 EI. So even before, so just when I had written down this, when I had drawn this diagram, I'm sure that many of you who had done well in GATE would have directly known the answer, but we should make a note that all of our sophisticated maths and whatever we have been discussing the past few lectures, it also gives us nicely that familiar undergraduate answer. Okay, so this was very easy warm-up example, just to show that what we have been discussing, it works. Now we can go to a slightly more, let's not say more involved, but slightly different kind of problem. So a simply supported beam. Okay, and we'll try to gradually see more and more involved examples. Okay, so again a beam, but this time simply supported. It's fixed at this end and it has a roller here. Okay, so overall it is very much statically determinate, and the point force that is acting again in the vertically downward direction, but perfectly at the midpoint here. Okay, so maybe this diagram is not perfectly accurate, but you get the sense. Let me just clarify the whole thing. So from here to here we again have this length L, and this distance, sorry about that. Okay, and of course this one has the magnitude P again, right? And again we are supposed to find out the deflection at the point of application of this force P in the same direction as this force is acting. Now as in the previous problem, our whole job will be effectively done the moment we find out what is the what is the bending moment expression. Okay, so what we'll do is this time we are going to consider the origin on our left hand side, so at this end with the x in this rightward direction, and what we are going to do is take a cut uh, take a cut like this, and we are going to consider this left portion, the left portion of this cut, the portion to the left of this cut. Now please note that what we plan to do here is to draw a free body diagram of this little portion. And when I say free body diagram, these reactions, the actual physical reactions, they should not be appearing. In its place, the reaction from this or the reaction force or forces from this end, that is what should be appearing. Now if you are a first year mechanics student, you would start out by writing a general horizontal direction force and a vertical direction force, and through force balance you would find out that that horizontal force is equal to 0. So I am going to skip a little bit and directly consider that horizontal force to be 0. So this is a free body diagram with the first year mechanics knowledge incorporated within it. Okay, so so we have this reaction force here, and sorry about that. I'll just redraw this thing. Okay, so we have this reaction force. Now, I'm sure that all of you would have figured out by now that the magnitude of this reaction force is going to be P by 2. It is going to be P by 2 because you note that at least in the vertical direction, this entire scenario is perfectly symmetric about this x equal to L by 2. So here it is going to be the reaction force, the vertically upward reaction force from this roller is going to be P by 2 upward, and from this end also it is going to be P by 2 upward. So here it is P by 2. Furthermore, again going by our positivity convention, our shear force will be like this and our bending moment will be in this sense. Okay, so this is our V and this is our M. And again, if we write the moment balance, what we'll obtain is M written like this. So considering this thing, this anti-clockwise sense, and if you consider the contribution to the moment from this P by 2 force about an axis passing through this end, it is going to be in the clockwise sense. So it's basically going to be M minus P by 2 times x, where of course this distance is x. Okay, so it is M minus P by 2 x is equal to 0. So that gives us M is equal to P by 2 x. That is fine. Now, specifically for this particular case, we can note that whatever happens from x equal to 0 to x equal to L by 2 is exactly what is going to happen from x equal to L to x equal to L by 2. So exploiting this symmetry, what we can do is for our deflection, which in general is like this, del del P of 0 to L, it's m square. So this basic formula, it remains the same for all beam problems. Of course, now what we can do here is to note that this 0 to L, it can basically be rewritten exploiting the symmetry of the problem in this fashion, twice of 0 to L by 2. All right. So now if we just substitute this expression for m here, you know that this 2 will cancel with this 2. So what we obtain here is just this del del P 0 to L by 2, and this m, it becomes P square x square by 4 EI dx. Furthermore, if we actually carry out this differentiation, we'll end up with 0 to L by 2 P x square by twice EI dx, and if we actually carry out the integration, we'll obtain P x cube 6 EI (0 to L by 2). And for our final answer, what we'll obtain is PL cube. So this 2 cube will give me an 8. So an 8 times 6 is 48. So this is PL cube by 48 EI. So again, I'm sure that many of you who have had a very good gate preparation, these answers, these very special case answers would be at your fingertips, and that's good, but it's also good that we know how to obtain this formally. Now please note that I have exploited the symmetry of the situation here like this. But what would happen perhaps if this case was not symmetric? For instance, if this P was not situated at x equal to L by 2, instead it was situated at some general distance A. Okay, so we can obtain, so we do have a more general method of obtaining the answer in those cases. So what we'll do is we'll discuss this general method for this particular example again. But what I will suggest is that once you get familiar with that method, and I suspect that quite a few of you would already know the method that I'm going to discuss. In any case, I will discuss it, and then perhaps people who are not that much familiar with that method, they can go on to apply that method to this more general case where P is situated not at x equal to L by 2 but at x equal to A. Okay, so the method that I'm talking about is basically using something called the singularity function or the Macaulay bracket. So basically it's like this, that suppose we do not exploit the symmetry, then what we have to do is we have to traverse the entire length of the beam from x equal to 0 to x equal to L, and in the process of doing that, the expression of the bending moment, that is going to change. Okay, because you note that from this 0 to L by 2, it is this P doesn't come into the picture. This externally applied P doesn't come into the picture. So if instead of taking the cut here, we were to take the cut here, then for that particular section, or this section, okay, this P would very much come into the picture, and then the free body diagram here would look completely different. Okay, so what I'm saying here is this, that if I were to take this cut here, then my section would look like this. Okay, the reaction force here would still very much be P by 2 here. That is not a problem. Sorry. That would have been P by 2 here, but we would also have the contribution from this downward force P, because now note that this entire thing is our x. Okay, and this is still L by 2. All right, so x is greater than L by 2. So the situation is a little bit different now. This is the same as before, the same convention, but now the expression for m will be different. Okay, so in what sense it will be different? It will be different because now m would be like this, contribution from here, the entire thing. But if we have to take the contribution from this P, it would be actually like P into x minus L by 2. So you note that x minus L by 2 is basically this distance, and I'm writing this with a plus here because the moment of this force P about an axis which is passing through this end would be in the same sense as that of this orange colored arrow, curved arrow, which represents our m. So our m is still like this. But note that if we just write up to this, it is not quite correct, because then that would mean that even when I am at this distance, it is perhaps like this. Okay, so to ensure, so if we can write it like this, with the understanding that if we keep on, if we say that x is indeed greater than L by 2, but suppose we want to write the overall thing, the overall general expression for m. So how do you connect this particular thing and this particular thing? So please note that this is correct for x is less than 2. So we connect these two things together by saying that m is so we write it like this, m minus p by 2x. That is not a problem. This one is like this, but multiplied with the step function or the Heaviside function. So this h, please note, this is the Heaviside function which contributes, like which makes the entire term contribute only when x is greater than L by 2, and that is equal to 0. Okay, so if we have this thing, if this kind of a term, then it is ensured that no matter where x is located, the expression for the m will come out as correct. Now this entire thing that I have written here, that can actually be captured by something called the singularity function, or something more familiar within the mechanics literature as a Macaulay bracket. Okay, so let me go to the next page. So this thing I will write as so these angular brackets, and conventionally we put a proper index here, which is the index 1, that's the power 1. So these angular brackets, it represents the Macaulay bracket. Okay, sometimes they're also referred to as the singularity functions. All right, so we can proceed like this. We can actually do the integration for this manually, and I myself used to do this thing. So I, at one point in time, I used to prefer this particular thing because I'm more familiar with the Heaviside thing, but it is very much possible to utilize a symbolic package like the symbolic Python within the Jupyter Notebook framework to very easily calculate these things. Okay, so as long as we are a little bit familiar with the terminology and the terms that we have to use there, so this can very well be done. So so let's see one example of this, how if we can actually recover this thing. Okay, so I have already tested it out here, so we can quickly use these things, but let me just demonstrate to you what is going on. Okay, so as afresh, so import sympy as sim, like we used to do in our applied elasticity course, and For those of you who may be not enrolled in this course but watching this YouTube video, some introductions to the Jupyter Notebook, to the use of Jupyter Notebook for these kinds of problems in solid mechanics, we have discussed in our previous course of applied elasticity, and even for students who are enrolled in this course, if you want to revise, you can take a look at those introductory lectures discussing the use of Jupyter Notebook and especially symbolic Python. But I am assuming that at least for all of you who are enrolled in this course, these things would be familiar. You have already done one term project involved using this, so it should be good. All right, so first of all, we import sympy, symbolic Python, with this alias sim. Next, we just set up our variables. So the things that we require are basically x, L, the length of the beam, the force P. But what I'll do is I'll set out this x separately. You'll realize why in a moment. So this L and P, I know for sure that they are positive entities, so I'll mention that explicitly. Okay, so all right, now what I really want to do is just this thing. Okay, what we were doing earlier, this u p bar is equal to del p 0 to L m square by twice ei dx. You note that irrespective of what this m expression is, involving Macaulay brackets or not, this can be simplified very generally as, if we do the integration, if we do the differentiation within the integration sign, then this basically comes out as your m by ei del m del p dx. Okay, so this is the general form, and I'm sure that many of you already know this. Nevertheless, this is the form that we're trying to achieve here, and you also note that there is this ei involved, but I have not written it here. Anyway, so what we would like to do is set up our integrand. Okay, so even before that, I'll just write this thing. So m into this. So this is what we want: the differentiation of our m with respect to p. So this is the form for the integrand. Okay, so I'm writing in a slightly haphazard fashion, but just to reflect my thought process. Now this m, this is the key thing to write here. So this m is equal to so if we take a quick look here, so this is m is equal to p by 2 times x. It's p by 2 times x minus the singularity function. Okay, so let's say that we use the placeholder term sf. Okay, please note this sf is not defined a priori, like as written sf. It is not defined like this within symbolic Python, but we are going to use an alias. So the important thing to note is that this is written in the form that so let me just quickly write down here that whenever you have this Macaulay bracket, the way Python understands this Macaulay bracket is that so you understand that there is an x here. So in general, if you have an x minus a to the power some n, so what Python will understand this as involving this one, and this one. So it's like a 3-parameter thing. Okay, but here of course our n is equal to 1, our a is equal to L by 2, and x is x. Okay, so let's see if we can write this down. Okay, so this is x comma L by 2 comma 1. Now SF, as I mentioned, is not predefined in this fashion. However, the singularity function, just like the Heaviside function, is very much defined within symbolic Python. So what we'll do is we'll import it from SymPy import singularity function, but use the alias SF, okay, so that we are free to use what we want to do in short later on. So this is the form of our for M. Now please note that I'll show you something. Okay, I'll come to the integrand part a little bit. So let's say that we write it like this. Okay, sorry, I did not press enter here. Okay, so suppose I want to display M. So you see, this is very nicely displayed. There's no problem. Now, what about this integrand? What does it show? Sorry, I have to write it as sim.diff. Okay, so it is showing us like this. Now, suppose we were to actually carry out this integration. Okay, suppose we were to carry out this integration from 0 to L. So sim.integrate, we put the integrand here. So that is basically m times del m del p. That is what the integrand is, and the limits of x from 0 to L. Okay, let's just see what happens here. Well, there is trouble. Okay, it's a bit problematic. So when I first tried to do this within symbolic Python, I also faced this kinds of problems. Now let's take a look at what I did to manage this thing. So you see, first of all, what I did here, oh sorry, I've forgotten to write one thing here. This is p into singularity function, because as you note here, this is m is equal to p by 2 into x minus p times this Macaulay bracket thing. Okay, so let's just run this thing once more. Okay, so that is our thing. So now you see the integrand is a little bit more complicated, and let's now see what it gives us. You see, if we don't help symbolic Python to simplify the things, it does this thing in all its generality, but this result is completely unusable. Okay, so what we can do is to help symbolic Python along its way. What we'll do is, instead of keeping our m just like this, and especially our integrand like this, so what I did here, you see that I have basically rewritten this integrand first of all piecewise, and then further simplified it. So this piecewise thing is something inbuilt within symbolic Python, and we can import it like this, and the result of it is that it basically outputs this term in a form which you would actually write if you are doing it in a calculus fashion with your own hand on a piece of paper. Okay, so let's try to do that. We go back to this line, we import this piecewise utility, and then let the m remain like this, but this integrand, I can keep it like that, this integrand that I will rewrite using the piecewise thing first. Okay, so let's just see what happens here. So it is somewhat better, but not quite. So let us simplify this further and see what happens. So this is much better. And now if we do this integration, you see very quickly it gives us the nice answer, PL cube by 48. Of course, I have not written this EI earlier, that I can quickly write down here, no problem. So this E, Young's modulus, the second moment of area, EI, all of them are positive entities, no problem there. So we'll keep this thing like this. The integrand, however, I'll just multiply by 1 by EI. Sorry, E times I. I didn't run this, I think. All right. Now it should give me the correct answer. That's it. All right. So because I have discussed so much in it, it may seem like a lot of steps, and I have also broken down the steps here. But in all, you can see that when I wrote it here, it was quite short. Okay. So for more complicated examples, and especially when you don't have the luxury of this this actually symmetric thing, then you will have a another parameter like A. So what I'm saying here is that if you go back to this diagram, and instead of this P located at L by 2, suppose it were located at some distance x equal to A, then carrying out this integration by hand would be quite involved, and then you will really reap the benefits of using this symbolic Python here. Okay, so on that note, I will end this video. Thank you very much, and I hope you'll get to explore this on your own furthermore.